Welcome to an exciting series on finding derivative of trigonometric functions. If you want to revisit this topic, this is the best place to start. We'll actually begin with concepts and fill in the gaps so that you can understand the topic very well. In case you want to learn from me, you can always send an email on the address given and we can enjoy the journey of success. Now let's see, how do we find derivative of trigonometric functions? I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll take up derivatives of trigonometric functions. Now this is a very important part of calculus which many students would like to revisit. I have kept that in mind and therefore designed a new curriculum for those who want to start again. So that is kind of important. You might have done calculus earlier. You may know the product rule, the quotient rule, the chain rule, but you might not remember the derivative of trigonometric functions. The whole idea here is to review and then recall what is expected. And if you are a beginner, even then you can begin with this particular video. So the idea here is that you can start finding derivative of trigonometric functions using this series. In case you really want to learn the topic, you can send an email on the address given to me. I'll be more than happy to guide you. As you can see in the contents, we are beginning to learn about the limits. As you know, derivative of trigonometric functions are defined only if the angle measurements are in radians. It's very important to understand that. A fundamental limit which is needed to understand the derivative is the limit sine x by x when x approaches 0. This limit is equal to 1. We'll prove it. Using this limit, we will also prove the second very important limit which is related to cosine x minus 1. We'll find the derivative of sine x using the first principle, that is to say, by definition. So you will recall that equation, difference quotient equation, correct? F of x plus h minus f of h over h when the limit of h approaches 0. We'll see how do we define the limit of this particular function and then get the derivative for sine x. Once we have found the derivative of sine x, we have opened the gates to learn derivatives of all the trigonometric functions. We'll begin with cos x and tan x. You can always find the derivative of secondary ratios using the strategies which we employ here. Basically, you'll have to use the product and the quotient rules. Then we'll give you some practice questions and worksheets. This playlist will have more than 6 videos where we'll answer some of the questions in your practice and worksheet and introduce to you new test questions. I hope you're ready for this exciting series on derivatives of trigonometric functions. So let's revisit what limits are. I'm going to go really fast on this. We have number of videos describing these topics. If this topic is new for you, I'd like you to go through these playlists, which you can type in my name, Anil Kumar, and the content of this topic, which is limits. Then you will get many videos on this particular topic to watch and understand the concept. Well, basically, limit of a function f of x when x approaches a, if it is equal to L. So that is how we write this limit, which is read as the limit of function f of x as x approaches a is L. So that is the nomenclature. A limit is the value that a function approaches as x approaches a specific value. X approaches a. That is how you have to read it. X gets closer and closer to the number a from either side, right? From both the sides. It has to approach from both the sides to the same value if the limit exists. From definition, the limit of the function may exist even if the function is not defined at x equals to a. Now this is extremely important concept. There could be a hole right at this point. Approaching means going very, very close, not just being there. You get the idea. If you can be there, nothing like it. Then it is a continuous function. Perfect. So now it's important to understand from the definition, the limit of a function may exist even if the function is not defined at x equals to a, provided the value of the function approaches L from both the sides. So you have to approach the same value from both the sides, correct? A limit is a value that a function approaches without necessarily being equal to as x approaches a specific value. So I hope that concept of limit is clear. Now let's see, how do we find limit of our function sine x over x? So as the definition explained, we'll now find the limit for sine x over x. Let's relook into the definition. Limit of a function exists at a if and only if the value of the function approaches a real value when x approaches arbitrarily close to a from both the sides. So what we are doing here is we are trying to approach x equals to 0 from both the sides. So when I write minus 1, it means from the left, and when I write plus 0 here, right, approaching 0 plus here, it means from the right hand side. Is that clear to you? Now since we are approaching 0, let us begin with minus 1 on the left side and plus 1 on the right side, and then we'll come closer and closer to x equals to 0. So look here, we want to approach 0. We are approaching from minus 1 and plus 1, going closer and closer to 0. That's the whole idea. So at x equals to minus 1, substitute the value. All these are in radians, important. So x is in radians, not in degrees. If you put x in degrees, you will not get the required result, and it doesn't really work out. And that is the reason why when we talk about derivatives of trigonometric functions, the units for the angle are radians. Is that absolutely clear? Perfect. So we are approaching from negative 1 and positive 1 the value of 0. Approaching really means closer and closer. So literally, we will evaluate the value sine x over x for minus 1, minus 0.1, minus 0.01, minus 0.001. You see how close as you can be. So that is the approach. Similarly, for right hand side, we are decreasing the value 1 to 0.1, 0.01, 0.001. You can now check the value. It is 0.99999, approaching 1. You get the idea. So from both the sides, we just approach a value 1, and therefore this limit exists and it is equal to 1. Is that clear to you? This is one of the most important limits when we consider derivatives of trigonometric function. The whole story starts from here, correct? So we got the limit sine x over x, where x approaches from left of 0 and from right of 0 the same value 1, and therefore the limit exists. Perfect. If there are any questions, you can put them in the comments. Let's continue. Now from here, let's go to the cosine function, another very important limit, which will now work out. Limit when theta approaches 0 for cos theta minus 1 over theta equals to 0. Now, if I substitute 0, then what do I get? I get cos 0 minus 1 over 0. And that is cos 0 is 1, 1 minus 1 over 0. We get 0 over 0. Now, this is indeterminate. Since this is an indeterminate form, we can find the limit, right? So let's see what strategy to apply. Rationalization, you remember that? Correct. So it's a review on the strategies applied to find the limit for indeterminate. Now we need to find the limit when theta approaches 0. What I'm doing to this function is multiplying and dividing by the conjugate of the numerator, which is cos theta plus 1. So multiply, divide by cos theta plus 1. The numerator, a plus b times a minus b, is a square minus b square, right? You remember? A plus b times a minus b is equal to a square minus b square. So therefore, when we do the rationalization in this form, cos theta minus 1 over theta times cos theta plus 1 over cos theta plus 1, we get cos square theta minus 1 over theta times cos theta plus 1. Do not expand the denominator. So what is cos square theta minus 1? Well, you remember this relation, sine square theta plus cos square theta is actually equal to 1. But we want to find what is cos square theta minus 1. So let me take sine square theta to the other side. It becomes negative sine square theta. This is important. Negative sine square theta comes in the denominator, comes in the numerator. Denominator remains same. Theta times cos theta plus 1. Now, negative can be taken outside. We have sine theta square, which could be written as sine theta times sine theta. You get the idea? And we have distributed the denominator as shown here. Smart move. This is in fact a very smart move. What that results into is that we can now use the laws of limit. Limit of the whole function is equal to the limit of individual parts and their addition and subtraction. So, minus outside, limit theta approaches 0 for sine theta over theta times limit theta approaches 0 for sine theta over cos theta minus 1 plus 1. Now we know that this limit is 1. We just proved it, correct? So, that is 1 for us. We can now substitute 0 for theta. Once you substitute 0, you get what? Sine of 0 is 1, correct? You know that. Sine of 0 is 1. Sine of 0 is 0 and cos of 0 is 1. Substituting those values, what you get is 0 over 1 plus 1, which is equal to 0. So we now know that the limit of this particular function, cos theta minus 1 over theta, is indeed equal to 0. Very important result which we are going to use many times in finding limits and also derivatives if you use first principle, or find the derivative using the definition. Now, as I was saying, it is very important to remember that the units are radians, and as you know, 1 degree is pi by 180 radians and 1 radian is 180 by pi degrees. The whole idea revolves around this circle. As you know, the total angle is 360 degrees, correct? Let me rewrite this. So the total angle when you measure is what? This angle is 360 degrees and is also equals to 2 pi. And that gives you the relation that 180 degrees is equal to pi. and that helps you to convert degrees to radians. Handy and useful. Now let us also look into the graphs of sine and cosine before we get into derivatives. When we see derivatives, it's kind of representing the value of the tangent at every point, right? So now look at the question. Sketch the derivative of f of x equals to sine x. So what it really means is to estimate slope of tangent. That can help, right? So that can result into the solution. So this is a sine graph for you, right? So the graph which we have given you is of sine x. Now if you sketch some derivatives, means the tangents, and find the slope, what do you get? Well, at this point, you can see the horizontal line. So that means the slope is 0. So on this graph, we have shown that slope 0. You get the idea. Then again, we have a slope of 0 here, and that is the next 0. Likewise, we can see that all these turning points result into the slope of 0. You get the idea. So the turning points result into the slope of 0. The maximum tangent slope is at this point, which happens to be 1, as shown here. So what you really see is that drawing tangents and noting their values results into a function, which is cosine of the function. So we can derive at the result that the derivative of sine is cosine. So these two functions, if you compare, then cosine x is the derivative of sine x, as each and every point on cosine x represents the derivative value of the tangent at any point on sine x. Very important visual to understand. Let's move on and recall derivative definition. As you learned earlier, g of x equals to limit h approaches 0, f of x plus h minus f of x over h. That is basically the definition of derivatives, right? Gradient of a function, the limiting value of the slope of the secant as tangent. That is what a gradient is called. Can be represented as limit of h approaches 0 of f of x plus h minus f of x over h. Right? This is a very important concept and is applied in many situations and is given a special name, derivative. That is what we explained in the beginning. Now, if you are revisiting this topic, it is important to recall, and therefore we have included this over here. So the derivative, which is written as f prime x equals to limit h approaches 0 for f of x plus h minus f of x over h, becomes the basic definition of derivative. So derivative at x equals to a is f prime of a. Replace x with a, correct? Which can represent the slope of tangent line or the instantaneous rate of change. Perfect. So I hope you recall this. Now let's continue with the derivatives. These are some other definitions which we normally use. I'll skip this and get into finding derivative for sine x. So from the definition, what is the derivative of sine x? Well, use the formula. From the first principle, f of x plus h minus fx over h, where the limit h approaches 0. This is what we need to calculate. What is f of x plus h when the function is sine x? Sine of x plus h minus sine x over h. And now we can expand this. So some of you may have to now recall trigonometry. So we remember the formula sine a plus b. Let me rewrite here. Sine a plus b is sine a cos b plus cos a sine b, right? So you may have to revisit these formulas, compound angle formulas, to continue. Correct. Now, for now, this is enough. Okay. So sine x plus h now can be expanded using this particular formula, sine x cos h plus cos x sine h. So that is the expansion of sine x plus h, right? Minus sine x. So we have this. Now we rearrange the terms, taking the term, separating this term out. You see that. And we have sine of xh cos of x on the left side. Now in this case, you can see that sine x is common. So since sine x is common, I've taken it out. We're left with cos h minus 1 over h. On the right hand side, I've taken away cos x. Since sine x and cos x are independent of h, you get the idea. Since they're independent, we can keep them away and find the limit of this particular function. You get the idea. So the limit for sine x when h approaches 0 and the limit of cos x when h approaches 0 is actually same as sine x or cos x. Correct? Because it is not dependent on h. On the other hand, the limit cos h minus 1 over h we figured out is 0. So we get a 0 there, and we know this limit is 1, and substituting the values, we get the derivative of sine x as cosine x. So the formula is derivative of sine x is cosine x. Is this derivation clear? I'd like you to pause the video, look at it, understand each and every step, and then move forward. You might have to find the derivative of secondary trigonometric ratios using first principle. Okay, exactly same steps. So that could be your exercise. Now let's move on and find derivative of cosine x. Okay, well, how do you find derivative of cosine x? We know the derivative of sine x, right? We just figured out the d dx of sine x is equal to cos x. We're going to use this. Well, cos x can be written as sine pi by 2 minus x. You remember the co-function identity, right? So in any triangle, as you can see, right angle triangle, if one of the angles is x, the other will be pi by 2 minus x. Now, if this is opposite, that becomes adjacent. So sine becomes cos. That is the concept. So sine, cos of x is sine of pi by 2 minus x. Now we can apply the derivative rules. Find the derivative. So dy dx is dy dx of sine of pi by 2 minus x, which is cos of pi by 2 minus x times derivative of inside function. That is the chain rule. And derivative of inside function minus x is minus 1. And therefore, we get minus 1 cos pi by 2 minus x. Now, cos of pi by 2 minus x is sine x. And therefore, we get our result, which is derivative of cos x is sine x. Perfect. I'd like you to go through this once again. Be sure that you understand. And then you can find derivative of other functions, right? So you can find derivative of, for example, secant x. I know that's a quotient rule. You can find derivative of cotangent x. You can find derivative of tangent x, and so on, correct? Now let's see. How do we find derivative of tangent x? So y equals to tan x can be written as y equals to sine x over cos x, and now we can apply the quotient rule. We know the derivative of sine and cosine, and that helps. Perfect. So applying the quotient rule, which means denominator square, and in the numerator, we have derivative of the first function times the second, first function times the second derivative with a negative sign in between. And then you get derivative of sine x as cos x times cos x is the first term, and the second term is sine x times derivative of cos x, which is minus sine x. Minus and minus becomes plus, and you get cos square x plus sine square x, which is 1 from the Pythagorean trigonometric ratio. In fact, it is one of the most important theorems for trigonometry. So you have 1 over cosecant square x, which is secant square s using reciprocal ratio. And so we get the derivative for tangent x, which is secant square x. Clear? So now I hope with this quotient rule, you can find derivative of all of the functions, okay? Well, once you find, you can check your values. So this is a summary for all the derivatives. I'd like you to actually find the derivative for cosecant x, secant x, and cotangent x. These are the values which you should match, correct? So exercise. So I should say, so practice. Find all the above derivatives. So that's important, right? And verify your result. That's the result. Second, when you move on from now onwards, you can use this as your formula sheet for derivatives of trigonometric functions. Clear? Now these are some questions for you to practice. We have y equals to, the question is, find the derivative dy dx of the following functions. Y equals to 5 sine 3x plus 2. Well, clearly, y prime will be what? Derivative of sine x is cosine x. We already have a constant here, and that gives you cos of 3x, and the derivative of inside function being 3, constant derivative is 0. So you get 5 times 3, 15 cos 3x as your result. Clear? So likewise, you can now do rest of the question, which will involve derivative rules. Apply them, and in case you have difficulty, you can always send an email to me on the address given, and we can discuss the possibilities of mutually learning. Now, once you do straightforward derivatives, here we have some application questions. When I say application, one of the major application is to find the equation of tangents and normal. So first 4 set of questions is basically finding equations of tangents and normals for different functions at different points. And then the last question here is an application question, which is a triangle has adjacent sides of 4 and 6 units with enclosed angle of theta. Prove that the triangle has maximum area when theta is pi by 2. So you can sketch and then you can do the needful to do this particular question, correct? So let us say that is the angle theta and the sides are 4 and 6. You can take this as a drawing and then continue to answer the question. With that, we end this video. We'll come up with more videos which will have solutions to these questions also. You can visit my YouTube channel and find many videos on derivatives of trigonometric functions. In case you want to learn from me, feel free to send an email on the address given. With that, we come to an end of this particular video, and we'll now begin with many examples and examination style test questions. I hope you liked and enjoyed this particular video, and if you are revisiting calculus and you want to learn all about derivatives of trigonometric and exponential and other difficult functions, then feel free to subscribe and write to me any particular things you have as questions. I'll be more than glad to answer your queries. Thanks for your time and all the best.